Definition of trigonometric identities. Welcome, everyone. In this first slide, we are setting the stage for our new topic, the definition of trigonometric identities. In this subsection, we are going to explore the fundamental concept of what we call identities, and more importantly, look at how this specific concept applies to the world of trigonometry. Now, before we jump into the complex formulas, I want you to pay close attention to the second point here. Understanding the precise difference between a standard equation and an identity is absolutely crucial. If you can grasp this distinction now, you will find it much easier to master the more complex derivations and mathematical proofs that we will be tackling later in this chapter. So, let's begin by defining what an identity actually is. 1. Understanding the concept of a mathematical identity. Now, before we dive straight into the complexities of trigonometry, I want us to take a step back and first understand what the term identity actually means in the broader context of general mathematics. You see, in your algebra classes, you have become very accustomed to encountering equations. However, there is a very special, more powerful type of equation known as an identity. So, how do we distinguish it? Here is the formal definition. An identity is an equation that remains true, no matter what values you assign to the variables involved. In other words, it isn't just true for one specific answer. It is a universal truth for the variables in that expression. Comparison between standard equation and identity. Now that we have established the general definition of an identity in the previous slide, let's look at a concrete comparison to see the difference in action. First, let's look at what we call a standard equation. Take, for example, the equation x plus 2 equals 5. Now, if you test this equation, you'll find it is only true if x equals 3. If we try to substitute other values, like x equals 1 or x equals 4, the equation becomes false. Because this statement is only true under a specific condition, specifically, when x is 3, we refer to this as a conditional equation. On the other hand, let's look at an identity. Consider the expression a plus b all squared, which equals a squared plus 2ab plus b squared. In this case, no matter what numbers you choose to assign to a and b, the left-hand side will always equal the right-hand side. Because this equality holds true for every possible value of a and b, we call it an identity. Keep this distinction in mind, because in the next slide, we are going to apply this exact same logic to trigonometric functions. 2. What is a trigonometric identity? Now that we have established the general mathematical meaning of an identity, remembering that it is an equation that remains true no matter what values we plug in, we can apply this exact same logic to the world of trigonometry. A trigonometric identity is simply an equation that involves trigonometric ratios, such as sine, cosine, or tangent, which holds true for every single value of the angle involved, as long as those specific ratios are actually defined for those values. To be more precise, let's look at the formal definition. A trigonometric identity is an equality involving trigonometric functions that is true for all values of the variable, which we usually represent as theta or the letter a, for which the functions are defined. As we will see in the next slide, we have to be careful with that last part about being defined, because there are certain angles where some of these functions simply cannot exist. The concept of permissible values. Now, before we move on to our practical examples, I want to draw your attention to a very important nuance in our formal definition. You might have noticed the phrase, for which the ratios are defined. This is a crucial qualifier. In mathematics, we have to be careful because some trigonometric ratios simply do not exist for certain angles. Let's look at a specific example, tangent theta. At 90 degrees, tangent theta is undefined. Why is that? Well, if we remember that tangent is the ratio of sine to cosine, we see that at 90 degrees, the cosine of 90 degrees is 0. Since division by 0 is mathematically impossible, the ratio fails to exist at that point. So, to keep our definitions mathematically sound, we must conclude that a trigonometric identity is true for all possible angles, with the sole exception of those specific angles where the functions involved become undefined. Keep this in mind, as it will be vital when we start verifying more complex identities in the next few slides. 3. Illustrative example: identity V's equation. Now that we have established the theoretical difference between a standard equation and an identity, let us move into a practical comparison. To clarify this distinction and see these concepts in action, let us look at two different trigonometric statements side by side. Case A, a trigonometric equation. Now that we understand the theoretical difference between an equation and an identity, let's look at a concrete example to see this distinction in action. On this slide, we are looking at case A, which represents a standard trigonometric equation. First, let's consider the statement, sine theta equals 0.5. To determine if this is an identity, we need to test different values for theta. In step 1, let's test theta equals 30 degrees. When we calculate the sine of 30 degrees, we get 0.5. So, for this specific value, the statement is true. However, we cannot stop there. To be an identity, it must work for every angle. So, in step 2, let's test theta equals 45 degrees. As we know, the sine of 45 degrees equals 1 over the square root of 2, which is approximately 0.707. This does not equal 0.5, so the statement is false for this angle. Therefore, our conclusion is clear. Because this equality is only true for specific, limited values of theta and fails for others, we classify this as a trigonometric equation rather than an identity. In the next slide, we will look at a much more powerful example that remains true no matter what angle we choose. Case B, a trigonometric identity. Now that we have seen how a standard equation only works for a specific value, let's look at case B, which is a perfect example of a trigonometric identity. First, let's consider the statement, sine squared theta plus cosine squared theta equals 1. To prove this is an identity, we need to see if it holds true for various angles, not just one. In step 1, let's test the angle theta equals 0 degrees. When we plug this in, we get sine of 0 degrees squared plus cosine of 0 degrees squared. Since sine of 0 degrees is 0 and cosine of 0 degrees is 1, the calculation becomes 0 squared plus 1 squared, which equals 1. So, the statement is true for 0 degrees. Moving to step 2, let's test theta equals 30 degrees. Here, we have sine of 30 degrees squared plus cosine of 30 degrees squared. We know that sine of 30 degrees is 1/2 and cosine of 30 degrees is the square root of 3 over 2. Squaring these gives us 1/4 plus 3/4, which, when added together, equals exactly 1. Again, the statement holds true. In step 3, let's try theta equals 45 degrees. We take sine of 45 degrees squared plus cosine of 45 degrees squared. Since both sine and cosine of 45 degrees are equal to 1 over the square root of 2, squaring them gives us 1/2 plus 1/2, which also equals 1. Based on these tests, we can reach our conclusion. Because this equality holds true for every angle theta that we choose to test, we can officially classify this as a trigonometric identity. This leads us directly into our next topic, where we will look at a real-world analogy to help solidify this concept. 4. Real-world analogy. Now, to help you truly grasp the difference between these two concepts, let's step away from the math for a moment and use a real-world analogy. Think of a trigonometric identity as a universal law. For instance, consider the scientific law that water freezes at 0 degrees Celsius at standard atmospheric pressure. This is like an identity because it is a constant, unchanging truth. It doesn't matter which specific sample of water you are testing, whether it's from a lake or a glass, the rule remains the same. In contrast, a standard equation is more like a specific condition. For example, if I say, the temperature in this room is 25 degrees Celsius, that statement is only true for this specific room at this exact moment. It isn't a universal truth that applies to every room in the world. Just like we saw in the previous examples with sine and cosine, an identity must hold true universally, whereas an equation only holds true under specific, limited circumstances. 5 common mistakes to avoid. First, be careful not to confuse standard equations with identities. It is a very common mistake to see any equation containing sine or cosine and immediately assume it is an identity. However, as we saw in our previous examples with sine theta equals 0.5, an equation is only true for specific cases. Always remember, for a statement to be an identity, it must hold true for all permissible values, not just one or two specific angles. Second, do not ignore domain restrictions. This is a subtle but vital point. As we discussed earlier regarding the definition of trigonometric ratios, identities are only valid where the ratios are actually defined. For instance, if you are working with an identity that involves tangent theta, you cannot evaluate or claim it holds true at theta equals 90 degrees, because tangent theta is undefined at that specific angle. Always keep an eye on where your functions might become undefined. Finally, a very important distinction to make is the difference between solving and proving. When you are solving a standard equation, your goal is to find a specific value for the variable, such as theta equals 30 degrees. But when you are proving an identity, your objective is entirely different. You aren't looking for a single answer. Instead, you are demonstrating through mathematical steps that the left-hand side is mathematically equivalent to the right-hand side, regardless of what value the variable takes. Now, before we wrap up today's lesson, I want to pause and highlight some common pitfalls. As you begin working through more complex problems, you might find yourself falling into these 3 common traps, so please pay close attention. Keep these distinctions in mind, and you will find the upcoming proofs much more manageable. Key takeaways. First, let's revisit the core definition of an identity. Remember, an identity is not just any equation. It is a special type of equation that remains true for all possible values of the variables involved. It is a universal truth within its context. Next, when we narrow our focus to trigonometric identities, we are looking at equations involving trigonometric ratios, like sine, cosine, or tangent, that hold true for every single angle, provided that those specific ratios are actually defined for those angles. This brings us to the concept of verification. As you progress through this chapter, you won't just be checking numbers, you will be asked to prove these identities. To verify an identity, your goal is to use algebraic manipulation to show that the left-hand side, or LHS, can be mathematically transformed to look exactly like the right-hand side, or RHS, you are essentially proving that both sides are mathematically equivalent. Finally, always keep the concept of constraints in mind. We must remember that identities are subject to the domains of the trigonometric functions. As we discussed earlier with the example of tangent, we cannot ignore that tangent theta is undefined at 90 degrees. Always be mindful of those specific angles where a function might not exist. All right, we have reached the end of this lesson. Let's take a moment to recap the key takeaways from today's session to ensure you have a solid foundation before we move on to more complex proofs in the next lesson. If you have mastered these fundamental definitions, you are now ready to tackle the actual derivation and proofing process. Great job today.